in electromagnetic waves and antenna theory course. So some of the point are like half-wave dipole antenna is simply a wire, you can say. You can say a transmission line, open-ended transmission line. When it is flared up completely, that starts radiating. Okay, so that is a dipole antenna, and we will see a very simple experiment we will be performing today. So first of all, we have to calculate the length of the half-wave dipole antenna, and this half-wave dipole antenna is a center-fed. All the half-wave dipole antennas are center-fed. That means it is fed to the center, and we will see how actually we can feed to the center of the dipole antenna, and finally we will observe that whether it is resonating at our desired frequency or not, and then followed by measurement of all these parameters. I mean, the radiation patterns, half power beam width, all those things. Okay, and radiation pattern, as you know, that the two perpendicular planes. In the H plane, you will get this type of radiation pattern, as you can see, unidirectional radiation pattern, and in the E plane, you will get what we say as figure of 8 radiation pattern. I think it is missing over here. Yes, this figure of 8 radiation pattern. Okay. First of all, let us begin our design. Let me go to the top. So over here, first of all, we will design a dipole antenna at 1 gigahertz. Okay, I have taken a problem of designing a wired dipole antenna for operation in 1 gigahertz. Okay, so corresponding to 1 gigahertz, first of all, you can find the free space wavelength lambda. Upon finding that lambda, you can calculate lambda by 2. Already I had done the calculation. You can do it yourself. What is lambda by 2 at 1 gigahertz? So lambda by 2 at 1 gigahertz is found to be 150 mm, right? And the wire should be as thin as possible. Okay. A very thin wire dipole antenna. So let us go to the design environment. You can see the design environment is like this. First of all, let us create the project template. Again, the same application we will choose microwaves and RF optical antennas. Then next, we will be designing wire antenna. So we have to carefully choose the template. So here you can see that wire option is there. So you can click on this wire. Then next, we will be doing the analysis in time domain. So time domain analysis. Next, all the dimensions, let us keep it as default. Since we are trying to design the antenna to radiate at 1 gigahertz, so let us choose the frequency window to be starting from 0.1 gigahertz to 4 gigahertz. Okay, such that 1 gigahertz is accommodated within that. Fine. Then click on next and then finish. Now the application is ready, template is ready. First of all, let us save this one, this particular project. Keep it under experiment number 2. Let me save it as E2. Okay, fine. So we are designing a wire dipole antenna, and we found the dimension to be equal to 150 mm. So since we are choosing wire, so simply it is a copper wire, and we can assume it to be like a cylinder. And so first of all, we will create a cylinder. You can see how we can create it. First of all, go to modeling and see. In the previous class, we were discussing about, all the structures were planar structure, and we had taken the option of brick. Now in today's class, we will be dealing with cylinder. So over here, you can see create a cylinder. So if you click on this drop down menu, two types of cylinders you can find, cylinder and elliptical cylinder. We will definitely choose cylinder, whose cross section is circle. Right. Press escape to show the dialog box. So let me press escape over here. We are creating a wire. So let us rename this cylinder as wire. And outer radius should be as thin as possible. So standard choice is to take the radius of the cylinder as 2.5 mm. And since we are not creating a hollow cylinder, so we will keep the inner radius to be equal to 0 mm. Right? Length of the cylinder is 150 mm. Okay, so if it is 150 mm, I want to orient. See, you can look into the coordinates over here. You can orient the cylinder along x axis, or you can orient it along y axis, or you can orient it along z axis. Okay, so let me orient it along z axis. The reason is to analyze the radiation pattern. If we take it along z axis, orient it along z axis, it will be easier for us. Okay, so 150 mm is the length of the cylinder. So I want to keep this wire symmetric with respect to the origin, right? That means I want to keep half of the cylinder in the positive z axis and half of the cylinder in the negative z axis. So for that, what we will do, minus 150 divided by 2, and z max will be 150 plus 150 divided by 2. Okay. Now under the material section, click on the drop down menu. There you will choose perfect electric conductor PEC, and for that, and all these things are over. And now click on OK, and you can see the cylinder is created. Now the thing is that, as I told at the beginning, it is a center fed dipole. So obviously your center should be, you have to cut some portion of the wire from the center such that you can connect the port. So for that, what you will do, you will again over here you have to click on this pick face center. We will not pick the whole face, rather we will pick on the face center. Okay, so click on this face center. Now place the cursor at this particular point. This whole face is now selected. Now double click, you will find a point is selected. This is automatically selecting the center of this particular face, right? Now the opposite face also need to be selected. For that you have to readjust the view, reset view. You can enable 3D rotation. So use your left click of the mouse and just rotate it such that other face is visible. Click on the zoom. Zoom in. The other face is visible. Follow the same steps. Go to simulation and pick face center. Other face is now selected. Double click. Now face center is selected. So the opposite face centers of the opposite faces are selected now. Now, unlike our previous experiment where we had taken the waveguide port, here we will not use that waveguide port, rather we will be using discrete port, right? So again, go to simulation. At the top, you will find just beside that waveguide port, there is an option called discrete port. Click on this discrete port. Okay. Now you can see over here, the discrete port has this type of window, small window. By default, the impedance of the discrete port is 50 ohms. So I have something to say about this. Okay, so let me go to the manual first, then we will change. Right. So I have already taken the screenshots and all. If you go through the manual, it will be very easy for you to construct. Okay. So over here, the discrete port part, you can see this particular window. Here, the impedance is 73 ohms. Can you tell me why instead of 50 ohms, we are taking the impedance to be 73 ohms? What is the radiation resistance of a lambda by 2 dipole? You had done a very long derivation, or not very long, a derivation in your previous semester, and you ended up with certain value. And there you may have already found that the radiation resistance of a lambda by 2 dipole antenna is close to 73 ohms. Okay, so it is for that reason the impedance is taken to be 73 ohms wave impedance. So you have to choose the wave port or in such a way such that the input impedance of the port and input impedance of the antenna matches, and that is actually is equal to 73 ohms. Okay, otherwise your matching will not be proper. Now click on apply and then OK. You can reset the view and your problem is ready over here. Now let us try to do the simulation. So go to simulation. You can go to setup solver and then start. So you can see your simulation is over. Then you have to observe the S11 parameter, whether we are getting the similar, I mean, a resonance as 1 gigahertz or something else. Let us see. Go to S11. Okay. So you can see the resonance is minus 10 dB over here. So you are getting some higher order resonance over above 2 gigahertz. So you can neglect this higher order resonance. The first resonant frequency is of our interest, and it is not at 1 gigahertz exactly. Okay, so that is the difference between the theoretical calculated value and the practical observation. Okay, you will get very close to 1 gigahertz, but not exactly 1 gigahertz. So what you have to do, you have to readjust the dimension by some, I mean, by some heat and trial process such that your resonance comes exactly at 1 gigahertz. Okay, so I have already done many calculations, and I had seen that if I take the length to be 120 mm, then the resonance is perfect. What is the reason behind that? If you go through any standard textbook, you will find that yes, we are taking lambda by 2 dipole, no problem with that. But actually, there is some impedance mismatch due to some inductance or a reactive impedance at the input impedance part. So for that to for minimizing that particular part, reactive part, we generally take a smaller length of the dipole. What I said, the input impedance has some reactive part. Now to nullify that reactive part, we have to reduce the length of the antenna such that your inductance will also will decrease. So if that decreases, that gets nullified, and generally if you take 0.4 lambda instead of 0.5 lambda, 0.5 lambda is itself means lambda by 2, then your resonance will be perfect. Okay, so it is seen that if I take it to be 120 mm, that means less than 0.5 lambda, a little less than 0.5 lambda, then your resonance will be perfect. So instead of 150 by 2 and 150 by 2, let me take 120 by 2, such that the length of the dipole is 120 by 2. Sorry, length of the dipole is 120 mm. So, okay, how I have done that, I have not shown. So what you have to do, go to the left in the navigation tree, expand. If your view is like this, then expand these components and then double click on the wire. Your history tree will open up. Then double click in this define cylinder. There you can edit the dimensions. Rest of the things are same. And if you take to reduce the length of this dipole 120 mm, then you can see that yes, you click on OK. Now the length of the wire gets reduced. Fine. So once it gets reduced, then you can re-perform the simulation. Okay. Now the second thing is that I do not want to see the second order resonance. So we can see second order resonance is occurring above 2 gigahertz. So let me decrease the frequency window such that your second order resonance is not visible. So for that, go to simulation. In the left, you can find the frequency. You can always edit the frequency. Initially, when we were preparing the template, we had taken the frequency window to be from 1.1 gigahertz to 4 gigahertz. Let us decrease it to 2 gigahertz. Okay. So click on this 2 gigahertz, and then you can re-perform the simulation. Okay. Now, before re-performing the simulation, let me do another change in the setting. Why? Because you want to know the radiation pattern also, right? So for that radiation pattern, you need to have the view of, you need to have some change in the setting. That means you need to go to field monitor. So at the top, under simulation in the toolbar, there is an option called field monitor. So go to this field monitor. So under this field monitor, you can find far field. So once you click on this field monitor, this small window will open up, and you can click on this far field. Okay, and you can always change the frequency. Since we are interested with 1 gigahertz, so let me make it exactly at 1 gigahertz. Click on apply. Yes, far field. And then click on OK. Fine. So your far field. See, in the navigation tree, you can find that far field monitor at frequency equal to 1 gigahertz is added. So we will now be able to see the radiation pattern at 1 gigahertz. Now reperform the simulation. Click on this setup solver, start simulation.
So far field f is equal to 1.05, no?
By default it was 1.05.
So we kept it 1.05. We don't have to change it.
No. I have changed it, right? See, far field equal to 1 gigahertz.
Okay, sir.
I've changed it because I want the observation at 1 gigahertz only.
Okay.
So this far field of all these things are not present in the manual.
Present, yes, it is present.
Okay.
Everything is present. Okay, now you can see that, yes.
Sir, actually, after simulation one error is coming. That software is licensed for up to only 1 lakh mesh cells only. The current mesh size exceeds this limit. Please reduce the mesh size accordingly. Sir, how do I do it?
In his simulation platform. Okay, so you have to reduce, you have to do some change in the setting. So what you will do, go to global properties. See, in the toolbar you will find one option called global properties. Click on that.
Sir, where?
In the toolbar you will find a global property. At the top, mesh view, then global property. Have you found it? Global properties. I can see your screen. Global properties. See,
on the right of mesh.
Green color.
Yes, mesh view, then global properties. Click on that. Have you found it?
No.
Somebody please
top right में देख, top right में देख.
6 वाले ऑप्शन के बगल.
Do you understand the toolbar? I mean,
mesh view में ना mesh view के राइट में है.
अभी सेटअप सॉल्वर है ना, उसी वाली रो में देख.
उसके बाद mesh view, उसके बाद global. ऊपर.
Sir, this one global property.
हाँ.
Only one global properties. Yes. Click on that. Click on that.
Sir,
You're not clicking on that. A small window has come up or not?
Sir, I have clicked, sir.
So once you have clicked on that, after clicking your new window that is coming up, it is not present. I mean, I cannot see that new window. It might happen that you have not presented your whole screen. Stop sharing and present the whole screen
Sir,
instead
I
of
am
a single.
presenting my whole.
Acha, anyone else can see the small window?
Sir, I am presenting.
एक बार फिर से कर
Yes.
स्टॉप शेयरिंग हाँ अब आ गया
Yes, sir. Okay, sir.
हाँ अभी अभी आ गया ठीक है नहीं अच्छा फिर से करो present your screen.
Sir, now can you see?
No, you present your screen. It is not visible. Go to present now.
Sir,
You
it
will
is
find
showing can't share your screen. So
the control is not in my
it is
hand.
showing. Sorry, an error when sharing.
Yes, share it once again.
Sir, again and again that same is coming.
Because
Sir, you can join again.
it is a general meeting, right? I have not done any host control. Anyone is the host. Dekho, somebody please help him. Okay, I will show you from my window. Okay, let me share my screen. You can change it accordingly. Your entire screen. Fine. So if someone faces that particular problem, I think every one of you have understood what type of problem he is facing. Then this particular is a software is a licensed version for student. Okay, you cannot use mesh cells more than 1 lakh. What is that mesh cells? All these structures can be divided into small blocks. So you cannot uh, use that beyond 1 lakh cell. So what change in setting you need to do? Go to global properties. You can see over here by default in my laptop it has taken the number of cells to be equal to 29496. So it is well below 1 lakh. So it is okay with this. So if somehow if you face that particular problem, you need to change that. So cells per wavelength, suppose for example, if it is cells per wavelength is say I am changing it to 20, for example. Okay, so click on apply. It is still 70. If cells per wavelength is 50, for example. So if cells per wavelength is 50, you can see number of cells. Go to the bottom part, you can see that number of cells is equal to 5,85,792. So it is well above the number of cells allowed for this licensed version. So what problem you will face? Click on OK. Let us click on setup solver and then start. Okay. So you can see the same type of error is coming. The software is licensed for up to 1 lakh mesh cells only. Okay. So for that you need to change the settings. So you have to go to global properties and cells per wavelength you need to reduce it. So I have already seen that if it is 10, then your number of cells is reduced. Even if it is 20, then also it is within the range of 1 lakh, 70,516. So accordingly you can change. You can change the number of cells per wavelength. You can reduce it and you can see what change in value is reflected under number of cells. So if that value is under 1 lakh, then your software will run. Okay, so that is yes.
Sir, my default cells per wavelength was 10. Then also it is showing 1,65,000. I reduced it to 5. Then it's also showing 1,48,000.
Reduce it to 3 or 2.
No, sir, no change. I reduced it to 1 even.
No change.
No change, sir.
Okay.
In the lowest value too, still it is showing 1,48,000.
So you click on apply and then see. Not only changing that
Yes,
value.
sir, I've clicked on apply and see.
So after changing it, we have to run the setup solver again, right?
Yes, definitely. After changing, once it is reduced to, okay, I will get back to you. Okay, so let me complete it. What is it? There may be some problem.
Your software licensed version of 2019.
Yes.
Okay, I think in the 2021 this problem occurred, I guess, because initially I also installed it and I faced that. It was a 2021 version. It's in my case. Don't know.
The same type of
Then
problem.
yes sir, मतलब 2021 वर्जन में इंस्टॉल किया था स्टूडेंट वर्जन, तो उसमें ये प्रॉब्लम हुआ था जो बैजन का हो रहा है, तो मैं उसे डिलीट करके 2019 वर्जन यूज किया. आई थिंक दैट कुड बी, आई डोंट नो.
अच्छा ठीक है, एक बार स्क्रीन शेयर करो तो फिर से, लेट मी सी. ओके, anyhow, so we were discussing about addition of the far field. Okay, it was not done. Fine. Now let us run the setup solver. Start. Simulation is over. Now under this navigation tree, click on this S parameter. You can see the resonance is coming almost at 1 gigahertz. Okay.
Sir, it's on 0.97. I also get that result.
No problem with that. So you can readjust the value. You can do many simulations. Okay. Even that is the thing. Actually, we are using this student version, and the accuracy is limited. Fine. If you use more number of cells per wavelength, your accuracy increases. So whatever, this is a good learning experience, no problem with that. So you are getting 0.97 gigahertz, very close to 1 gigahertz. So you can even change the length to 119. You can see what change you are getting. So that is up to you. Now the thing is that we have to see the radiation pattern at 1 gigahertz. Now the question may pop up into your mind that yes, at 1 gigahertz you are not getting the resonance, but still you can see at 1 gigahertz the curve is below minus 10 dB. So that is acceptable, no problem with that. So let us see. So go to the navigation tree, and you can see over here at the bottom part there is an option called far field. Expand that far field, and you can see far field f is equal to 1 indicates far field at 1 gigahertz. Fine. So if you click on this far field itself, you will get a 3D radiation pattern. So the 3D radiation pattern you can see, enable this 3D rotation, and you can see that it is almost like an apple. Okay. So what we used to do in finding the 2D radiation pattern in our previous electromagnetic waves and antenna classes. So actually we see the cross sections of two perpendicular planes. What is the meaning of that? See, two perpendicular plane means if you cut this radiation pattern along YZ plane, try to understand my point. If you cut this radiation pattern along YZ plane, you will get some cross section. And if you cut this radiation pattern along XY plane, then if you look from the top, you will get a pattern. Fine. Now, once you cut this radiation pattern along YZ plane, then definitely it will be a figure of 8. Why? Because you can see a dip at the top. See? If you see, you can see a dip, right? But when you look it from the top, see XY. If you cut along XY, there is no dip. So it is exactly a circle. So how to do that? How to observe that 2D radiation patterns, specifically E-plane radiation pattern and H-plane radiation pattern that you had seen in theory. Now you are trying to have a practical view of that, right? See over here under this far field, if you click on this absolute part, no change. Fine, click on this, right click over this far field. Then go to far field properties. This particular window will pop up. See in the top left corner of this small window, you can see that by default 3D is selected. But if you want to look into this 2D radiation pattern in polar plot, because we used to find the radiation pattern in polar plots in angles. Okay, so click on this polar. Now once you click on this polar, then exactly at the right, what angle you will vary by keeping what angle constant. Try to understand this particular point. Okay, for that you need to origin access plot mode. Fine. Just a second. We must understand one small thing very carefully. Okay. Now over here, this is X, and say it is Y, and you have Z like this. So X, Y, Z. Now, how the angle varies, try to understand. See, if you go from Z towards X, then you are varying theta. So theta varies from Z to X. So at Z, theta is equal to 0, and at once you reach at X, it becomes 90 degree. Similarly, if you go from X towards Y, then what happens? Then you are varying phi. So that means phi at X is equal to 0 degree, and when you reach at Y, it becomes 90 degree. Now you have to understand that where your dipole is oriented. Okay, your dipole is oriented along Z, like this. Your dipole is oriented like this. Now your dipole will have some radiation pattern. So your radiation pattern, so if you want to, you have to find the radiation pattern in two different planes, in XZ plane and XY plane. So if you find the radiation pattern, sorry, is phi, and your dipole is oriented exactly like this. Now, in the XZ plane, how your radiation pattern will look like? Your radiation pattern in the XZ plane will look like this. Almost like a figure of 8 pattern. Please excuse me for the drawing. You can see. So how do you if you want to see the radiation pattern in the XZ plane, what setting you need to do? You have to vary angle theta, right? You have to vary in the XZ plane, in XZ plane. You need to do vary angle theta. Okay. Keep phi equal to 0 degree. Try to understand, because your phi at X is equal to 0 degree. In XZ plane, you have to vary angle theta by keeping phi is equal to 0 degree. And next radiation pattern in other principal plane, that means in XY plane. So in XY plane, what you will do? In XY plane, you have to vary angle phi and keep theta equal to 90 degree. I hope you have understood, right? Popularly, this XZ plane radiation pattern is also called E plane radiation pattern. It is also called E plane radiation pattern. Fine. E plane whatever. Anyhow, I removed this one. The first one is the E plane radiation pattern, and second one is the H plane radiation pattern. So accordingly, we will vary this. Fine. So I hope you have taken a note of this. So here, what we will do, suppose if I want to find the E-plane radiation pattern. So what change I need to do? I have to vary angle theta by keeping
Y0.
phi equal to 0 degree. So if it is equal to 0 degree, just click on apply and then OK. Okay. So you can find a figure of 8 kind of thing radiation pattern. So what you will do, you will take a print screen of this particular diagram and you will paste it, right, in the frequency that will be given to you. Okay. Now the next part of the problem is, once you find this E-plane radiation pattern, you have to find the 3 dB beam width. See, 3 dB beam width, why it is 3 dB beam width, all those things, I leave it as an exercise for you. You can revisit your previous class, why it is 3 dB, right? This software automatically calculates that 3 dB beam width and it is equal to 80.9 degree. You can see 80.9 degree. So you can take this particular reading and you can paste it in your report. Now the second thing, you have to find the radiation pattern in other principal plane, that is H-plane pattern. So for that again you need to go to this far field properties, and there you have to vary angle phi by keeping theta is equal to 90 degree. So once you keep it as 90 degree, you click on apply. See, omnidirectional radiation pattern is obtained, right? So here in this omnidirectional radiation pattern, you need not have to find the 3 dB beam width because it is not directional, it is omnidirectional. So in the E-plane radiation pattern, you are getting directional radiation pattern. There you will find 3 dB beam width, okay, or half power beam width. 3 dB beam width is also called half power beam width. You know what is the reason behind that? Do you know or not? Half power beam width is also called 3 dB beam width. In AEC classes, frequency analysis of transistors, when you studied about 3 dB bandwidth or half power bandwidth. So that 3 dB concept remains same. Okay. Anyhow, you read that what is the meaning of 3 dB beam width and all, or else we can discuss in the next class. So this is how we find the radiation pattern. Now next thing is directivity. How do we find the directivity, right, at 1 gigahertz? So what you will do, go to the top, go to, is that directivity automatically calculated? Let me see. No. Okay, go to post processing. Then you will find an option in the toolbar called result templates. Go to result templates. Far field and antenna properties is automatically there. There will be 2 drop down menus. So keep the option in the first drop down menu as it is, far field and antenna properties. And in the next drop down menu, click on this. You will find an option called far field results. So far field and antenna properties and then far field results. So once you click on that, you will find directivity. Try to understand this point. So once if it is omnidirectional, that is when you are seeing the H-plane radiation pattern, you need not have to find the directivity. Directivity is 1 in that case. Okay, but when you find the directivity for directional patterns, definitely you will get some value, more than 1. So let us see what you are getting. So click on this all settings. Now polar constant phi is equal to 0. Keep theta is equal to 90 degree. Plot mode, it is already directivity. So keep this setting as it is. Click on OK. Now you can see, you can calculate, evaluate. So let me check it out. I think it is in single direction. Sorry. See, you can see the directivity is 2.14 dB. So you can check it with your theoretical result. Check it over here. You can see one thing, very interesting. Uh, the theoretical value, directivity of a theoretical value of directivity is 1.64. Okay, but practically you are getting 1.62. Here you can find that it is 2.14 dB, no problem with that. So a small mistake I have done. So what you need to do is that just click on this setting, keep it as it is. Just click on this 3D. Now the question arises, why you are actually clicking on this 3D? Because this 3D will take, three-dimensional radiation pattern will take care of all the possible direction in 3D. So obviously your directivity will be maximum in the direction of maximum radiation. So automatically that will be taken care of in this 3D radiation pattern. Okay, so that is why let us click on this directivity 3D. Okay, so I have done it in the manual. Do not worry about that. Click on this again. Just hold on for 2 seconds. Maximum value. Right. Very interesting result you are getting. See, I'm deleting all these things. In the manual, you have got 1.64. Go to far field and then the far field result. Then all settings. So directivity is in the direction of maximum radiation. Click on this 3D and in the result value, if you click on this maximum value, because directivity is maximum in the direction of maximum radiation. So maximum value. Now in the plot mode, you have got directivity. Now in the plot mode, if you click on this plot mode, then by default it is in dB. Okay. So you are getting the result in dB. So I have done the calculation in linear value, not in dB. That is why the calculation was 1.62. Okay. But if you calculate in dB, it will be 2.15 dB theoretically. So plot mode is directly in dB. So let us keep it as default. Now, why I have told that interesting value we are getting? See, 3D radiation pattern 5, it is okay. Let us click on this OK and just evaluate. What value you are getting? 2.14 dB. Okay, that is in accordance with your theoretical value that you have obtained. Now, one thing I had done previously, That is in single direction. That was also correct because we already know what is the maximum direction, isn't it? What is the maximum direction? The maximum direction is phi is equal to 0 degree and theta is equal to 90 degree. So along this particular direction, your radiation is maximum. Now, if you click on this OK and then evaluate, then also you are getting same result. So in either of these two ways, you can calculate. Okay, so this is directivity. Fine. Thank you very much. So I hope you have understood today's experiment.
Excuse me, sir.
Yes.
Sir, I got an error that the variable frequency value is greater than the reference value. So how you saw means did you get that or how to solve it?
Share your screen.
Minimum is 0.1, maximum is 4. This is okay, sir, but still it's showing that that the reference frequency value is greater than the observed frequency f equal to 1. I don't know what's
So is it that 1.0 or 10 that you check it?
no,
You
it's showing that reference frequency is 2.05 and field monitor frequency is 1.0. So it cannot be done. It's saying. So I don't
What
know.
is that reference frequency that you are? So reference frequency option is not showing in this window.
Okay, so I'm trying to.
You try it. You check your
Yes.
manual. Okay.
Okay, sir.
Actually, I cannot hold the meeting for a long time. I have a meeting.
Yes, sir. Yes, sir.
Join in
Sure.
that. Okay.
Okay.
So today's experiment is a very simple experiment. I hope everyone has understood, and I have prepared the manual in a very lucid way. Each and every steps are explained in a very clear fashion. No one will have any difficulty if you follow that. So I will be sending you the task just after this meeting. Here you need to design the dipole antenna not at 1 gigahertz but in some other frequencies. So accordingly you have to design and you have to perform the experiment. Okay. Thank you very much.
Thank you.
Thank you, sir.